Welcome to the course on Python for data analytics, machine learning and generative AI. In this video, we are going to learn about Numpy library in Python, the bedrock of high performance computing. In this video, we will cover what is Numpy, core components of Numpy, array creation and access, understanding the array, assembling, deconstructing with joins and splits, refining the form through sort, search and filter, from arithmetic to advanced math, and generating and structuring random data. By the end of this video, you will have a clear understanding of what is Numpy. Numpy is the foundation of high performance computing in Python. Most popular libraries like Pandas, SciPy, scikit-learn, matplotlib, and TensorFlow are built on top of Numpy. At the core of Numpy is the ndarray or n-dimensional array. If you want speed, efficiency, and scalability in data science or machine learning, Numpy is essential. By mastering Numpy, you unlock Python's true power of scientific and numerical computing. The Numpy array, also called ndarray, it is a fast, memory-efficient container for large data sets. Unlike Python, list all elements in a Numpy array are of the same data type. This allows Numpy to store data in continuous memory blocks. Because of this, Numpy operations can be up to 50 times faster than Python loops. Let's see how to create Numpy arrays and access their data using indexing and slicing. Let's break down step by step with clear examples. First, we create a two-dimensional array using np.array of 1, 2, 3 and 4, 5, 6, which forms a grid with 2 rows and 3 columns. In Numpy, indexing starts from 0. So each element is identified by its row and column positions. To access a single value, we use indexing. For example, data of 1, 1 selects the element in the second row and second column, which returns the value 5. To access multiple values at once, we use slicing. For instance, data of 0 means select all rows from the first column and this returns the array 1, 4. Together, indexing and slicing allow us to efficiently extract individual elements or entire sections of data, which is essential for numerical computing and data analysis in Python. Every Numpy array has a shape and a data type called dtype. The shape tells us the size of the array in each dimension. The dtype defines the type of data stored like integers or floats. We also learn the difference between a view and a copy. Changes in a view affects the original array, while a copy remains independent. The reshape function lets us change the shape of an array without changing its data. The total number of elements must remain the same. Here, a 1D array is reshaped into 2D and even 3D arrays. Reshaping is very useful in machine learning and deep learning. It helps prepare data for models without copying memory. Numpy allows us to combine arrays using join operations. Functions like concatenate and stack help merge arrays. We can also split arrays into smaller parts using split or array_split. Joining is useful when combining data sets. Splitting is helpful when dividing data for training and testing. The 3 common data operations are sort, search, and filter. Sorting arranges data in ascending or descending order. Searching finds indices where a condition is true. Filtering creates a new array that satisfies a condition. These operations are widely used in data analysis workflows. Universal functions or ufuncs perform operations elements by element. They replace slow Python loops with fast C-based executions. This makes NumPy code cleaner, much faster. Operations like addition or multiplication happen in one line. Vectorization is one of the biggest advantages of NumPy. NumPy provides a wide range of mathematical functions. These include arithmetic, aggregation, rounding, and trigonometry. You can compute sums, logarithms, sine, cosine, and more. NumPy also supports GCD and LCM operations. This makes NumPy suitable for both basic and advanced math. NumPy also supports set-like operations on arrays. Unique removes duplicate values. Union 1D of finds values present in either arrays. Intersect 1D of finds common values. Set difference 1D of finds values present in one array but not the other. Those functions are very useful in data cleaning and pre-processing. NumPy helps us simulate real-world uncertainty using the numpy.random module. Random data plays a critical role in statistics, machine learning, and scientific modeling, allowing us to test ideas when real data is limited or expensive. With NumPy, we can generate random samples to prototype algorithms, simulate complex systems like financial markets or physical processors, and apply techniques such as bootstrapping for statistical inference. Think of numpy.random as a controlled way to introduce chance into our models, helping us explore patterns, variability, and risk in a mathematically sound and computationally efficient way. NumPy generates and organizes randomness. Functions like randoff create values uniformly between 0 and 1, with randnoff draws samples from a standard normal distribution, commonly used in statistics. For discrete values, randindoff generates random integers within a given range. Beyond generation, NumPy also lets us structure randomness. The shuffleoff function rearranges elements in place, modifying the original array, while permutations returns a shuffled copy, leaving the original untouched. These tools are essential for tasks like random sampling, data shuffling, before training models and running fair simulations. Data distributions describe how probabilities are spread across possible outcomes. Many real-world phenomena follow recognizable patterns. The normal distribution or bell curve is symmetric and centered around a mean, appearing in measurements like height or blood pressure. The uniform distribution assigns equal probability to all outcomes, making it useful for unbiased sampling. The binomial distribution models the number of successors in repeated independent trials, such as coin flips. Understanding these fundamental distributions helps us choose the right mathematical model to represent real-world data accurately. NumPy supports a rich gallery of advanced probability distribution. The Poisson distribution models how often events occur in a fixed interval, such as customer arrivals. The exponential distribution captures time between events, while the chi-square distribution is widely used in hypothetical testing. Logistic and multinomial distributions are key in machine learning and classification problems. Others like Pareto, SIF, Rayleigh describe wealth inequality, word frequencies, and natural phenomena like wind speeds. These distributions allow us to model complex, real-world behaviors with precision and flexibility. Let's now have a quick summary on what we have covered in Python NumPy. NumPy, the numerical Python, is the foundational library for numerical and scientific computing in Python. At its core is the n-dimensional array ndarray, a fast memory-efficient data structure that enables high-performance operations on large data sets. Numpy supports vectorized computation, allowing mathematical operations to be applied to entire arrays at once, making code cleaner and significantly faster than traditional Python loops. It provides powerful tools for array creation, indexing, slicing, reshaping, and broadcasting, along with a rich collection of mathematical functions, including arithmetic, linear algebra, statistics, and universal functions. Numpy also includes random number generation and probability distribution for simulation and modeling. Serving as the backbone of Python data ecosystem, Numpy underpins libraries such as Pandas, Scipy, Matplotlib, scikit-learn, TensorFlow, and PyTorch, making it essential for data analysis, machine learning, and scientific research. So, let's open Jupyter Notebook and write some Python code together and bring the concept of Python NumPy to practice. Thank you.